Now let's look at how changing some other variables affect the benefits. So we'll go ahead and write down our current irrigation and water quality benefits from our 4-acre reservoir in our base scenario so that we can compare later scenarios. So with that, we'll scroll back up to our list of inputs, and we'll start by changing our reservoir depth to 12 and leave all other inputs the same. And we'll scroll back down and select Run Edward. Okay, now that we have our results from our second scenario where we've increased our reservoir depth, we can go ahead and look at applied irrigation. And so our reservoir of 4 acres now is able to supply 5.6 inches of irrigation on average. For our ARIS value, we now have a value of 0.77. And for our nitrate load reduction percentage, our value for our 4-acre reservoir is 42%. So why the increase? Well, starting with irrigation benefits, remember in our base scenario, we noted that irrigation benefits generally increase with reservoir size. This is because larger reservoirs have a greater water supply and can therefore supply more water for that supplemental irrigation. In this example, we've increased reservoir size, but in terms of depth rather than surface area. So in cases where we may be limited in terms of surface area footprint of a planned reservoir, we may still be able to increase the water storage potential by making that reservoir deeper. Now for water quality, the increased load reduction occurs because, one, if the reservoir has a larger volume or capacity to store drained water from the field, then we can capture and store more nutrients from the field. And second, if we can increase water use from the reservoir, then we're able to create additional storage capacity within the reservoir for capturing and storing later drainage events. So a reservoir's overall storage volume is an important variable in determining potential irrigation and water quality benefits, but also the amount of water use within the system is an important part of leveraging that overall storage volume. Now let's look at how this reservoir would perform on a different soil type with different soil water characteristics. So we'll scroll back up to the input menus. Note that our current soil type is silty clay loam. Now if we click on the advanced settings, in the top left we can see under soil profile settings our profile field capacity and wilting point. These values determine the range of volumetric soil water content where plant available water is held in the soil. This range is also often defined as the water holding capacity or the available water holding capacity of the soil profile. In EDWRD, we use standard default values that are populated based on the soil type that was selected on the previous screen. So if we go back to the previous screen and now select silt loam and open advanced settings, we can see that these numbers have changed. If you've done your own soil measurements, you could also change these default values, but we'll keep our default values for this example. So in this example, we're essentially changing the capacity of the soil profile for holding plant available water, and also at what range of soil water contents plants can access that water. So we'll close this input window and run EDWRD with our silt loam soil. Alright, so now we have our results for our 4-acre reservoir with an average depth of 12 feet, but now on a silt loam soil rather than a silty clay loam soil. And so if we look at applied irrigation for our 4-acre reservoir, we see that our irrigation decreased from 5.6 to 5.5 on average. For our annual relative irrigation supply, we have increased from 0.77 now to 0.81, which is above our original design target of 0.8. And if we look at nitrate load reductions on a percent basis, we can see that we've stayed essentially the same. We've increased slightly from 42.12 to 42.16. So to break this down a little bit, with our silt loam soil, we see slightly less irrigation on average, but greater values of annual relative irrigation supply. So in this case, our silt loam soil can hold soil water and plants can access that soil water a little bit better than on silty clay loam soil from our first two examples. There's less irrigation required, and what irrigation is supplied meets a greater proportion of that overall irrigation requirement. In terms of water quality, remember that reservoir volume and water use strongly factor into creating the potential to capture and store water and nutrients from the field. And since these factors didn't really change that much for this example, our nutrient load reduction stayed pretty much the same. And so for our last example, we're going to go ahead and take a look at our irrigation management approach. So if we scroll back up, now let's change our irrigation approach from applying fixed 1-inch irrigation amounts to now letting that applied irrigation amount vary. And for this, we'll refill soil capacity to 70% of the water holding capacity of the soil. And so the actual amount of irrigation will vary depending on the estimated soil water content at that time of irrigation, as well as the severity of the deficit water condition. So let's go back down and select Run EDWRD. All right, so we have our results. And so this scenario, we have a 4-acre reservoir that we're evaluating with an average depth of 12 feet on a silt loam soil. And our irrigation management approach is now set to variable in that we'll be applying enough irrigation to refill to 70% of water holding capacity. And so if we look at applied irrigation for that 4-acre reservoir, now we've increased from 5.5 inches from before to now 5.63. If we look at annual relative irrigation supply, this is also increased now from 0.81 to 0.84. And if we look at nitrate load reduction on a percent basis, we'll see that we've increased from about 42% to now 43%. So by changing our irrigation management, we've been able to move the needle a little bit to increase both our irrigation and water quality benefits without modifying anything about our reservoir, our soil, or our crop conditions. And so the reason here goes back to our original point about the amount of water use being an important variable in determining our potential irrigation and water quality benefits. Now in this case, just by looking at our average annual water use, we don't see that much of a change. However, if we dig in a little bit deeper into how that water use occurs throughout the year, we'll see that the timing and magnitude of our irrigation events also influences these benefits. So in this specific case, with choosing to irrigate enough to refill our soil profile to 70% of water holding capacity versus just applying standard 1-inch applications, our irrigation events throughout the year become less frequent but in greater amounts. And so this led to slight improvements across the board in terms of total irrigation amount applied, annual relative irrigation supply, and nutrient load reductions. And so for a more detailed look at the field and reservoir water balances of the system and how benefits are being generated, you could download the daily, monthly, or annual results from EDWRD and look at these for yourself. And so I hope you've enjoyed this example exercise and learned a little bit more about how to use EDWRD to quantify the potential irrigation and water quality benefits of drainage water recycling. Thank you.